Two geometrical objects are called similar if they both have the same shape, or one has the same shape as the mirror image of the other. More precisely, one can be obtained from the other by uniformly scaling, possibly with additional translation, rotation and reflection. This means that either object can be rescaled, repositioned, and reflected, so as to coincide precisely with the other object. If two objects are similar, each is congruent to the result of a particular uniform scaling of the other. A modern and novel perspective of similarity is to consider geometrical objects similar if one appears congruent to the other when zoomed in or out, at some level. For example, all circles are similar to each other, all squares are similar to each other, and all equilateral triangles are similar to each other. On the other hand, ellipses are not all similar to each other, rectangles are not all similar to each other, and isosceles triangles are not all similar to each other. If two angles of a triangle have measures equal to the measures of two angles of another triangle, then the triangles are similar. Corresponding sides of similar polygons are in proportion, and corresponding angles of similar polygons have the same measure. This article assumes that a scaling can have a scale factor of 1, so that all congruent shapes are also similar. But some school textbooks specifically exclude congruent triangles from their definition of similar triangles by insisting that the sizes must be different if the triangles are to qualify as similar. Similar triangles. In geometry, two triangles and are similar if and only if corresponding angles have the same measure. This implies that they are similar if and only if the lengths of corresponding sides are proportional. It can be shown that two triangles having congruent angles are similar, that is, the corresponding sides can be proved to be proportional. This is known as the Aaa Similarity Theorem. Due to this theorem, several authors simplify the definition of similar triangles to only require that the corresponding three angles are congruent. There are several statements, each of which is necessary and sufficient for two triangles to be similar. 1. The triangles have two congruent angles, which in Euclidean geometry implies that all their angles are congruent. That is, if is equal in measure 2, and is equal in measure 2, then this implies that is equal in measure 2 and the triangles are similar. 2. All the corresponding sides have lengths in the same ratio. This is equivalent to saying that one triangle is an enlargement of the other. 3. Two sides have lengths in the same ratio, and the angles included between these sides have the same measure. For instance, and is equal in measure 2. This is known as the Aaa Similarity Criterion. When two triangles are similar, one writes, there are several elementary results concerning similar triangles in Euclidean geometry. Any two equilateral triangles are similar. Two triangles, both similar to a third triangle, are similar to each other. Corresponding altitudes of similar triangles have the same ratio as the corresponding sides. Two right triangles are similar if the hypotenuse and one other side have lengths in the same ratio. Given a triangle and a line segment, one can, with straight edge and compass, find a point F such that the statement that the point F satisfying this condition exists is Wallace's postulate and is logically equivalent to Euclid's parallel postulate. In hyperbolic geometry, similar triangles are congruent. In the axiomatic treatment of Euclidean geometry given by G.D. Birkhoff, the Aaa Similarity Criterion given above was used to replace both Euclid's parallel postulate and the Aaa axiom, which enabled the dramatic shortening of Hilbert's axioms. Other similar polygons. The concept of similarity extends to polygons with more than three sides. Given any two similar polygons, corresponding sides taken in the same sequence are proportional and corresponding angles taken in the same sequence are equal in measure. However, proportionality of corresponding sides is not by itself sufficient to prove similarity for polygons beyond triangles. Likewise, equality of all angles in sequence is not sufficient to guarantee similarity. A sufficient condition for similarity of polygons is that corresponding sides and diagonals are proportional. Similar curves. Several types of curves have the property that all examples of that type are similar to each other. These include circles, parabolas, hyperbolas of a specific eccentricity, ellipses of a specific eccentricity, catenaries, graphs of the logarithm function for different bases, graphs of the exponential function for different bases, logarithmic spirals. Similarity in Euclidean space. A similarity of a Euclidean space is a bijection f from the space onto itself that multiplies all distances by the same positive real number r, so that for any 2 points x and y we have where d is the Euclidean distance from x to y. The scalar r has many names in the literature, including the ratio of similarity, the stretching factor, and the similarity coefficient. When r equals 1, a similarity is called an isometry. Two sets are called similar if one is the image of the other under a similarity. As a map, a similarity of ratio r takes the form where is an orthogonal matrix and is a translation vector. Similarities preserve planes, lines, perpendicularity, parallelism, midpoints, inequalities between distances and line segments. The similarities of Euclidean space form a group under the operation of composition called the similarities group S. The direct similitudes form a normal subgroup of S, and the Euclidean group E of isometries also forms a normal subgroup. The similarities group S is itself a subgroup of the affine group, so every similarity is an affine transformation. One can view the Euclidean plane as the complex plane, that is, as a two-dimensional space over the rails. The 2D similarity transformations can then be expressed in terms of complex arithmetic and are given by n where a and b are complex numbers. A0. When a equals 1, these similarities are isometries, ratios of sides, of areas, and of volumes. The ratio between the areas of similar figures is equal to the square of the ratio of corresponding lengths of those figures. The altitudes of similar triangles are in the same ratio as corresponding sides. If a triangle has a side of length b and an altitude drawn to that side of length h, then a similar triangle with corresponding side of length kb will have an altitude drawn to that side of length kh. The area of the first triangle is A equals bh2, while the area of the similar triangle will be A asterisk equals 2 equals k2a. Similar figures which can be decomposed into similar triangles will have areas related in the same way. The relationship holds for figures that are not rectifiable as well. The ratio between the volumes of similar figures is equal to the cube of the ratio of corresponding lengths of those figures. Galileo's square-cube law concerns similar solids. Similarity in general metric spaces. In a general metric space, an exact similitude is a function f from the metric space X into itself that multiplies all distances by the same positive scalar r, called f's contraction factor, so that for any 2 points x and y we have weaker versions of similarity would for instance have f be a bi-Lipschitz function and the scalar ra. Limit. This weaker version applies when the metric is an effective resistance on a topologically self-similar set. A self-similar subset of a metric space is a set K for which there exists a finite set of similitudes with contraction factors such that K is the unique compact subset of X for which these self-similar sets have a self-similar measure with dimension d given by the formula, which is often equal to the set's Hausdorff dimension and packing dimension. If the overlaps between the are small, we have the following simple formula for the measure. Topology. In topology, a metric space can be constructed by defining a similarity instead of a distance. The similarity is a function such that its value is greater when 2 points are closer. The definition of the similarity can vary among authors, depending on which properties are desired. The basic common properties are positive defined, measured by the similarity of one element on itself, and more properties can be invoked, such as reflectivity. The upper value is often set at 1. Self-similarity. Self-similarity means that a pattern is non-trivially similar to itself, e.g., the set 0.5, 0.75, 1, 1.5, 2, 3, 4, 6, 8, 12 of numbers of the form where range is over all integers. When this set is plotted on a logarithmic scale, it has one-dimensional translational symmetry. Adding or subtracting the logarithm of 2 to the logarithm of one of these numbers produces the logarithm of another of these numbers. In the given set of numbers themselves, this corresponds to a similarity transformation in which the numbers are multiplied or divided by 2.